me see. Okay, thank you. Well, of course, nothing can begin without the commercial. So here's the commercial. This is the interactive fractal. So you can see the fractal there. And this is the interactive globe. Well, you can point to anywhere on the Earth and get a real nice picture out of it. Okay, $5 each. I think it's, if you want to take a look, or I can show you on my computer, but not at this time. Okay, so here is the presentation, Harvard to Princeton at Stanford. Okay, the problem that I have been challenged is to make a very simple force system for Arduino. Okay, so I did Arduino eForth, but that was from what I learned from Bill. But that was using assembler. And using assembler, then you have basically you have to have some programming tool to download the binary. So here, you know, this is my old setup. We have the Arduino there, and it has a USB cable to the PC. But you need a programmer there so that you can download the fourth program into the 80 mega 328. So that was my setup to make full use of the microprocessor and eForth. So you have to have this link. And but I think I was challenged, especially by Masa, that can't you just get rid of this thing and use this set alone? And I say yes and no. So the idea is that if you can just make it, use this connection alone and to interact with the Arduino. Yes, we can always do it. No, we cannot do it because this link, you have to go through the USB interface on the Arduino board in order to write new code into the flash here. But the strange thing about it is that to do that, you need have a downloader on this chip. And the downloader sits in the bootload section of the flash memory. If you want to write anything into the application flash, the code has to be in the bootloader. And when I do the force system, I just take over the bootloader entirely. So I have a section, some code in the bootloader, so I can write new code in the flash. But without the taking over the bootloader, you really cannot write anything in the flash. So here, if we use the Arduino, and we have to have the bootloader there, so you cannot write new code into the flash. And that was the problem. But the last month when we discussed, people said, well, can't you just use the RAM to store new code? Yeah, yes, you can do it. But you only got 2K bytes of RAM. And of that 2K bytes, only about 1.5 kilobytes are available. So you can have a very small memory area that you can put new code in. Yes, there's no problem in putting new code in. You cannot put the real code in the flash memory because Arduino or the 80 mega 328 does not execute anything of the RAM. If you want to execute any real code, it has to be in the flash. Okay? But we can always build a virtual force machine. And with a virtual force machine, well, you can do anything, right? So that's the idea. So the problem is that 18Mag328 is a microprocessor of Harvard architecture. So it has a separate program memory and data memory. And you can read and write only into the data memory. And you can execute only from flash memory. And the flash memory is 16-bit units. And the RAM memory is in 8-bit bytes. So they are the two different memory spaces. And C also, well, we want to do anything compatible with Arduino, it has to be written in C. And C is a programming language also of Harvard architecture. You can, in C or all the conventional programming language, you really don't know where your program is. Okay? And why don't you have to know? No, you don't have to know. And all you have to do is declare some arrays, some variables, and then once you declared it very politely, then you are allowed to read or store into these areas. So that's a Harvard architecture. But eForth is basically a Princeton architecture. It doesn't care where things are stored. You can store anything, you can read anything, you can write anything, you can execute anything. And that's the basic architecture of eForth. So what we want to do is use a Harvard architecture microprocessor and use a Harvard architecture programming language and really do a Princeton architecture system. And this is how you can do it. Build a eForth virtual machine. And this eForth virtual machine is actually modeled after EP32 or whatever. And that has its origin in MUP21, which Chuck designed originally. So, in basically emulate this machine in eForth using the C programming language. And so we need 33, actually only 30 pseudo instructions. And these are the machine instructions for the eForth virtual machine. When we designed the EP32, yes, we designed these things as actual machine instructions. But here, in a virtual machine, we use pseudo instructions. And pseudo instructions are stored it can be stored in program space or stored in the data space. And it is bytecode, okay? And actually, we only need 5 bits, but give it a byte anyway. Inside the eForth virtual machine, there's a finite state machine. And this finite state machine will go into the memory and fetch out the pseudo instructions, execute it, and then fetch out the next one. So just like a real machine, but it has an instruction set you can design any way you want. But with about 30 pseudo instructions, we can build a complete eForth virtual machine. And on top of the eForth virtual machine, we impose a dictionary. And that contains the entire eForth code. So to make it work, then we have to have a unified memory model. So this model will span both the flash memory space and the RAM space using the same instructions, fetch and store, cfetch and cstore. So these memory instructions, pseudo instructions, are smart in that they can determine whether you are fetching or store into from a RAM memory or fetch from a flash memory. So, and with this unified memory model with a single set of instructions which can access both RAM and flash memory, you can actually build a eForth system which is extendable. So originally, if you boot up, all the instructions are in the dictionary, which is in Flash, and which is in as a C data structure. Okay, everything's stored there. But when you are running it, you can extend that dictionary in the RAM memory because it's just data. Okay, you can add more data in the RAM memory and link this data to the dictionary in the Flash, and you can grow it just as normally what you would do with eForth. Okay, of course, eForth commands are linked into a dictionary, but since we have a unified memory model, we have the set of instructions which can access both memory areas, and then there's no problem in growing the dictionary into the RAM memory. Okay, and the command, of course, have a record, the link field, name field, and code field. And we have two different kinds of commands, a primitive commands, which has only bytecode or pseudo instruction in its code field. And compound command, which the high-level colon definitions, and you have a token list. And the tokens are just addresses in the addresses that in the unified memory model. Okay, so the the final system I built called the eForth _ 328, and it is written in a sketch. The sketch is Arduino program that you can compile and run. Pseudo instructions are code in C. Finite state machine are also code in C. A dictionary, which is in a data structure and data array. And this data array is produced by a metacompiler and imported or copied into the sketch as a data array. And with that, we have a complete system. And the memory space in this model, uniformed memory model, from 0 to FF, that's the 80 meg 328 registers. Okay, and the first 32 bytes are actually mapped into the 80 meg 328 CPU registers. And then the next to FF, these are I/O registers. Okay, and from 100 to 2FF, this is a data space assigned by C. So, I have no way of knowing what's in it. But I look in the memory map and so, well, this is, I didn't put anything there, so it must be put up by the C compiler. But from 300 and up, that seems to be free. Okay, I poke and peek, and nothing serious happened. So I use the first 32 byte to store or initialize them to false variables, and the next whole bunch of memory, about 1.5 kilobytes of free space, which you can grow the dictionary. And on top of the memory map, there is an area where the TIB, terminal input buffer, and also the ATM hardware stack are there. So as long as you stay within this area, it's safe. Okay, you can read and write and do anything you want, but just keep away from the other area, and the eForth is running just fine. And from 900 up to 1FFF, this is where the dictionary, original dictionary is, which is stored in the flash memory. Okay, so finite state machine, let's don't worry about that. And this is the metacompiler. This is how you generate that data array. And this metacompiler is originally coded by Chuck for MUP21, but I've been using it for most of the other processors I work with. And this metacompiler is really very nice, and it works very well to build the fourth machine there. Okay, so let's don't spend any more time. I just want to show you here. This guy is running, and so here it works, and yeah. Okay, if you you can do all the other things, but I think you guys have all seen this scene. So thank you very much for your time. Okay. Any questions? Yes.
Can you comment a little bit about the performance you're getting?
This is about 4 times slower than the fourth system that's written in assembly. So only 4 times slower. But that's what you pay when you code everything in C. Yes. Oh, yes.
Most of them are in the architecture.
That's the next speaker, so.
Yeah. Okay.
You can ask
Yes.
him that.
Right. Yes. Yeah. The answer is yes.
Yeah, in fact, eForth is done exactly that way. What I'm doing is I'm giving
Okay.
hand with
Yeah.
creating the fourth dictionary.
Yeah. So I have a version of fourth which is coded in C, and that can be ported to any other system. Yeah. Okay. Thank you. Yeah, John.